Hi everyone, this video is going to talk specifically about nuclear particles. A lot of these that you're going to be able to find on Table O. This is not comprehensive of everything on Table O, but it does talk about the most common types of decay, and it compares some of those particles that are being released by unstable nuclei. So we're going to focus on four different particles or types of radiation here, all of which can be found on Table O, and we're going to kind of compare and contrast their properties. So the first type of decay that we'll take a look at is alpha decay. And then when something decays via alpha decay, it means it releases one of these alpha particles. And you can see alpha radiation is denoted using that little alpha symbol that looks kind of like a hybrid A and a fish kind of combined together. We're going to use the notation 4/2 He or 4/2 alpha to represent any alpha particle in any equation that you may be writing. Either one is fine. All that means is that this particle has a mass of 4 and a charge of +2. This stands in contrast to the smaller beta particle, which again, if you look on Table O, you're going to see that a beta particle is signified by the beta symbol and a minus. And that minus is important for reasons that we'll see in just a second. But what we find is that the beta particle actually looks a whole lot like an electron, because check it out, it's got no mass and a charge of -1, just like an electron in a regular atom. Now, it's a little weird because we're talking about nuclear stuff, but bear with me. Beta particles look a lot like electrons in that they have 0 mass and a charge of -1, and that's actually why we write the E there, oftentimes when you see a beta particle denoted. Positron decay releases a positron, which is not only the coolest word in Regents chemistry, but it kind of stands in contrast to our beta radiation. So if you look down on Table O, positron is the last one listed there. And it looks a little funky, kind of like the opposite of a beta particle, where we've got the beta symbol, but then it's positive. So it still has no mass, but it now has a charge of +1, which is a strange looking thing, but that's okay. You can just write it straight off of Table O and know if something is decaying by positron decay, this is the particle that it is releasing. The last type of radiation you're actually not going to find listed on Table N when you look up the decay modes of a number of radioisotopes. However, it is an important type of radiation to know about because it's kind of infamous in its kind of associated dangers of exposure. Gamma radiation. Gamma radiation has no mass and no charge, which is why I don't represent it as a particle, but rather kind of as like waves. And it's going to be denoted using this gamma symbol, right? And what you're going to find when we sort of compare the properties of these four different types of radiation is that as we decrease in mass, we're actually decreasing in the relative power of those radioactive things. So what I mean by that, if we go back up to our alpha radiation, these three lines represent three different substances. This gray line is just paper. This brown line represents something like aluminum foil. And this black line represents maybe a lead sheet. So if you've ever been to the dentist, you know they put that like lead vest on you before they give you x-rays. There's good reason behind that, and this is it. So if I allow something to decay via alpha decay, that alpha particle hits paper and it kind of gets blocked. So if you want to protect yourself from alpha radiation, carry around a wad of paper with you. Beta and positron radiation are a little bit hardier. They're a little bit smaller, so they can move a little bit faster. And they're going to only be able to be stopped by something along the lines of aluminum foil. So they can pass right through paper, but they take a little bit of force to be able to stop them. You can kind of think about this as if I was trying to get something from one room to another, I'd have to go through the wall. This is like throwing a big old basketball. It's just going to bounce right off. This is like shooting some kind of like BB gun. You might make a little bit of progress, but you're still probably not going to make it all the way through. However, Gamma radiation, having no mass and no charge, is extremely powerful. Gamma radiation can pass right through paper, right through aluminum, and some of it can even get a little bit through lead, but most of it is going to be stopped if your sheet of lead is thick enough. If we go back to our analogy, this is kind of like screaming at the top of your lungs. Your scream has no mass and no charge, but if you're screaming loud enough, even the person in the next room can hear you. So the way we talk about these contrasting properties is by this kind of property of penetrating power. The more mass you have and the more corresponding charge, whether it's positive or negative, results in lower penetrating power. So that big bulky alpha particle is not able to pierce through as much as your small massless gamma radiation. So keep those terms in mind, what all of those types of radiation look like in their notations on table O, and also this idea of penetrating power. Which one is the most powerful? What can pierce through the most?